Welcome to This Explainer. Today, we're tracing a truly massive trajectory, the evolution of a scientific powerhouse from its ancient foundational roots, literally all the way up to today's cutting-edge breakthroughs. Whether you're a history buff curious about early tech, or you're fascinated by the complex systems driving global innovation right now, the scope of this journey is just immense. So let's dive right in. It's a huge question, right? How exactly do you build a scientific powerhouse? To really understand this, we have to look past just the sheer volume of achievements making headlines today. We actually need to examine both the deep historical legacy that set the whole precedent for discovery and the massive, highly organized ecosystem driving that engine of innovation today. It's like a giant puzzle of history, infrastructure, and human capital. Okay, here is our roadmap for today. 1. Ancient foundations of science. 2. Space, physics, and computing. 3. Life, earth, and energy. And finally, 4. The innovation ecosystem. Moving right into Section 1, Ancient Foundations of Science. Now, we're not just talking about old tools here. These are the literal building blocks of global modernization. Think about it. The invention of paper and woodblock printing, which eventually evolved into early movable type printing, completely revolutionized how human knowledge was recorded and shared. It spread ideas like wildfire. Then you've got compasses and gunpowder, which changed navigation and chemistry forever. And by periods 4 and 5, we see this profound shift towards systematically observing the natural world. Take the ancient earthquake detector or seismoscope, for example. It was this brilliant device featuring bronze dragons dropping metal balls into toads' mouths to indicate the exact direction of an earthquake. I mean, how cool is that? These innovations absolutely formed the bedrock of the early scientific method. But, early science wasn't just about observation and record keeping. Massive hydraulic engineering systems for managing water, paired with the methodical development of traditional medicine, these really demonstrate a deep-rooted focus on applied problem solving. This was science used directly for everyday survival, for agriculture, and for health. It laid down a highly practical mindset that echoes directly into the modern day. Let's fast forward a bit. Section 2, Space, Physics, and Computing. Just take a look at the sheer scale of these cosmic milestones. This isn't piecemeal. It's a highly comprehensive end-to-end strategy. It starts right here in Earth's orbit, with an active human spaceflight program, space station construction, and spacewalk missions. But it extends way, way further out. We're talking about developing independent satellite navigation systems, executing lunar exploration missions, including that remarkably complex Farside moon landing, and even successfully deploying a Mars rover mission. And all of this is underpinned by advanced rocket launch technology and dedicated deep space research. Meanwhile, back on Earth, in the realm of physics and computing, a fascinating dual focus is clearly taking shape. On one hand, you have massive physical infrastructure. Think aggressive supercomputer development, robotics, and intensive semiconductor research. But running directly in parallel to this heavy hardware is the mastery of intangible, invisible networks. We're talking about quantum communication experiments and quantum satellite research, literally pushing the absolute boundaries of physics. Combine all that with massive 5G technology deployment and AI research expansion, and you get a society that is rapidly digitizing its entire physical footprint. Which brings us to Section 3, Life, Earth, and Energy. Here we are seeing parallel advancements actively tackling massive global challenges simultaneously. In the medical and biological sciences, you've got robust public health research, like pioneering malaria treatments and vaccine development, running alongside cutting-edge genomics and the integration of medical AI systems. Now, apply that same high-tech approach to agricultural science. Famous breakthroughs in hybrid rice and crop genetics are being paired with modern soil improvement and smart farming automation to ensure global food security. It's really a dual-pronged approach to sustaining human life on a massive scale. Zooming out to the environment around us, these engineering and earth science achievements highlight a huge push to monitor the natural world while physically connecting urban environments. On the monitoring side, there are advanced earthquake and weather forecasting systems, alongside extensive geological surveys. They're even conducting scientific ocean exploration and establishing a real research presence in the Arctic and Antarctic. And on the engineering side, the scale is just staggering. High-speed rail networks crisscrossing the landscape, mega dam engineering, and highly advanced bridge and tunnel engineering science. This is literally the science of reshaping and understanding the physical world on a macro level. But to power all of this requires a total revolution in energy. From intense solar energy research and wind energy development to hydropower engineering, maximizing water resources, and battery innovation driving electric vehicle technology, well, these sectors aren't operating in isolation. They combine with active carbon reduction technologies to form a massive, unified push towards renewable energy expansion and green manufacturing on a global scale. It's the whole shebang. All right, let's pull back the curtain. Section 4, the innovation ecosystem. You see, none of the breakthroughs we've looked at today happen by accident, and they certainly don't happen in a vacuum. They are the direct result of national research collaboration and, above all, long-term scientific planning. This is all about treating science not just as some academic pursuit, but as a core, foundational pillar of national development. The structural components dedicated to talent development and innovation are staggering. It starts with the rapid expansion of research-oriented engineering universities and massive, large-scale STEM education. But it doesn't stop at graduation. A vast infrastructure waits to absorb that talent. National research laboratories, science parks, and technology incubators, all fueled by a massive expansion in research funding. Add active international scientific collaboration to the mix, and you see a machine designed specifically to accelerate actual, real-world technologies. But, as we know, infrastructure needs a culture to really thrive in. Beyond just the funding and the physical labs, there is a deliberate cultural push to foster scientific literacy. The promotion of STEM education starts early, driven by youth science competitions, interactive science museums, and widespread exhibitions. This fosters a mindset that naturally feeds into technology entrepreneurship growth and super tight collaboration between industry and universities. The ultimate result of this deep cultural integration? A tremendously large, highly skilled engineering workforce ready to tackle the problems of tomorrow. Which brings us to our final thought. We've traced the path from ancient movable type printing and bronze seismoscopes to quantum satellites and AI-driven smart cities. As we look at this massive, meticulously constructed engine of education, culture, and infrastructure, it leaves us with a compelling question. What will the next chapter of this long-term scientific planning yield for global innovation? Because if this trajectory tells us anything, it's that the pace of discovery is only going to accelerate. Thank you so much for joining me on this explainer, and remember to keep questioning the world around you.